the subgoal panel is only displayed when it's in the middle of, when the cursor is actually in the middle of a proof that's halfway checked. So it may be that it's correctly blank, and you just need to move to a different part of the file. Okay, other last questions? Good. Let's move on to induction. Okay, I'm going to skip this. Okay, separate compilation. Again, you've probably mostly encountered this already and solved it, but this will be the place where things will get messed up. This line will be the place where things will get messed up if you're having search path problems. And I'll just tell you my favorite way for solving them is the way that things are compiled if you do it directly from the IDE, either coq IDE or proof general, treats the paths a little bit differently and produces a different .vo file than if you say make at the command line. So if you see messages about, blah blah says basics, but something else has top.basics, try removing all the .vo files and starting again. If in your IDE you ask it to accept this line, it will automatically recompile the basics file for you if it needs to be recompiled. So just throwing away the .vo file and asking it to process this line will have the side effect of recompiling basics in the right way. Okay. Proof by induction. Obviously, once we have definitions by recursion, we need to prove things about them using induction. Once in a while, you can prove something about natural numbers using just a destruct, but not for very interesting function definitions. So almost always, you need to use induction. And here is the principle of induction for natural numbers. It says, if we have a proposition involving a number, so we have a proposition about a number n, and we want to show that this proposition P holds no matter what n is, we have to do two things. We have to show that P holds of 0, and we have to show that P holds of n prime under the assumption that it holds for, we have to show that it holds for successor of n prime under the assumption that it holds for n prime. If we can do those things, then it holds for all n. So this is exactly the natural number induction principle that everybody is familiar with from discrete math. The only difference in coq is that it isn't a kind of special thing that's only for numbers. It's something that is generated every time you give an inductive definition. So the keyword inductive, when accepted by coq, automatically generates an induction principle that for the natural numbers is exactly this, and for other structured data types like trees or whatever is the appropriate thing for that type. So every inductive definition comes with an induction principle, and we can access that induction principle in various ways, but the simplest one is using the induction tactic. So the induction tactic is like destruct. It's exactly like destruct, except that it binds one more thing in cases that are where the data type, the inductive declaration is properly inductive. That is, one of the arguments to a constructor is the type that's being inductively defined. Then we're going to get an extra variable, which by convention I usually call IH something something to remember that that this variable is representing the induction hypothesis. Okay, now I have a question for you. No, I'm going to answer it myself. I'm not going to do this one together in class because I want to get through all of these 3 chapters and we're running out of time. But I will gladly answer questions at any point. Okay. We can structure proofs in coq in many ways. One simple way that's often useful is writing a quick lemma inside of a proof and immediately proving it right there and then going on to use it. So this tactic, assert, says, I want you to do two things. I want you to create a sub-goal asking me to prove this. And then once it's proved, I want you to give it the name h and allow me to use h in the rest of the proof. Actually, I might have said that backwards. Maybe the sub-goal of proving h comes second, and the use of h in the rest of the proof comes first. In any case, you get two sub-goals, one to prove h and the other assuming h. So it's just a way of splitting a proof into a subsidiary fact and a use of that fact. And I'm going to skip over that. Okay. A little discussion about formal proof versus informal proof. So informal proof is what we do on paper and what mathematicians do in textbooks and what computer scientists do in the papers that they write. And its purpose is similar to the purpose of a formal proof, but not exactly the same. So strictly speaking, the purpose of a formal proof is to get the proof checker to say yes. And you can interpret it as saying something about a mathematical truth, but really it's just a program that's driving the proof checker through a sequence of states and getting it to a state where it has no sub-goals. As such, a formal proof tends to be a rather low-level thing, just as a realization of some distributed protocol in C tends to include a lot of details that are important to get the thing to run, but that are not actually that germane to understanding the main functioning of the protocol in your mind. So proofs and programs can be used in different ways for different purposes. They can be used for establishing truth in the case of proofs. They can be used for creating behaviors in the case of programs. They can be used for communicating belief or instilling belief in another person in the case of proofs. And they can be used for communicating understanding in the case of programs. And these are related activities, but not the same. It's important to realize that because it's easy to fall into the trap of thinking that when you've proved something formally, you understand it, which isn't always the case, or even worse, that handing somebody a formal proof helps them understand something, which is typically not ever the case. So formal proofs always need to be accompanied by explanations, intuitions, comments, good naming, splitting things up into nice structures, and so on, all the same sorts of things that we do with informal proofs. Let's see, I wanted to say one more thing. Yes, this realization of the kind of sharp divide between formal and informal proofs came as somewhat of a disappointment to me about a couple of years after I wrote the first version of what became the Software Foundation series. So my idea originally, I had been teaching from an older textbook that I had written that only had paper proofs, and that covers a lot of the same material. I've been teaching that for many years, and I was frustrated with the fact that a lot of people coming to my course didn't understand how a proof worked, didn't understand how to think about proofs for one reason or another. And I really felt like I didn't have the energy or the number of TAs needed to help everybody with that problem. Just like if we were teaching a course about history, and people came not knowing how to structure sentences in English, it would be pretty hard to kind of help them with those grammatical problems at the same time as teaching them how to write papers about history. So the idea of software foundations, the original kind of rallying cry was one TA per student, and the TA is called coq. I think that was a good idea, but it only worked about 80%. So I think coq is good for teaching people how to think about proofs, but it's good for teaching people how to think about formal proofs, not how to think about informal proofs. Writing good informal proofs is a question of communication, it's a question of writing, it's a question of conveying understanding from one human mind to another. And that is just a different process from the hacking that's involved in getting formal proofs to work. So the point of that sermon is formal proofs are good and useful, but don't think that they're all there is to life. It's also important to learn how to abstract from those formal proofs and communicate ideas. And that's a kind of a separate process. All right. And that's the end of that chapter. Any questions? Okay. Last chapter for this morning, for this part of this morning, is lists. So we wouldn't get very far programming in any functional programming language or any other programming language without data structures. We've seen ways of defining numbers. Here are some more interesting ways of putting together structured data. So numbers were in some sense already a form of structured data because each number that isn't 0 has a number inside it. So you can think of a number as a list of S's. And indeed, that's a useful way to think of it. But we would like to have lists of other things. We would like to have pairs. We would like to have other data structures, trees, whatever. So here is a type of pairs. So this is a constructor that takes 2 arguments. And it's interesting as an inductive type because it only has 1 constructor. So every value of type natprod has the constructor pair sitting at the top. But of course, that pair can be applied to any 2 numbers, and that's what's interesting. So when we pattern match against a pair, there's only 1 clause in the pattern. And the interesting thing that we're doing is binding the variables in that pattern clause, which we can then use on the right-hand side. As for other things that we've defined, we can define notation for pairs. So we'll define the usual parenthesis with comma in the middle notation for pairs. And we can use it, interestingly, both on the right-hand sides and on the left-hand sides of pattern matches. So we can write pair syntax also in pair patterns, and that's quite useful for making things readable. All right. Here's a simple thing we would like to show about pairs, that every pair is equal to the pair of its first projection and its second projection. And this proof is very easy if we write the theorem in this kind of peculiar way. But a nicer way to write the theorem is this, that anything of type pair is equal to its own the pair of its own first and second projections. And this doesn't simplify, so reflexivity does not prove it. How do we prove it? With destruct. So once again, destruct is our friend. Okay, here going on from pairs to lists. So here is a properly inductive type of lists of natural numbers. It has a constructor nil and a constructor cons. The constructor cons takes a nat and a nat list. And we can have some familiar notation. We use double colon for the cons symbol because single colon, which would be more familiar for Haskellers, is used for type of in coq. And we use square brackets. And by the way, we use semicolon instead of comma for separating the elements of a list. I don't know exactly why they made that decision early on, but that's the way it's done in coq. And then with those things in hand, we can write some useful recursive functions over lists. And once again, this is completely familiar for those of you that are experienced functional programmers. So here is the repeat function that takes a number n and a count, which is the number of times to repeat it, and returns a list of that many copies. Here is the length function. Here is the append function. And here is some special syntax for it because we use it a lot. Here is head and tail. But here we run into a little discussion about coq's, about the fact that coq is total. So the tail function looks exactly like the tail that we would write in ML or Haskell, but the head function has a default argument. So it has to take two arguments, the list that we're taking the head of and the thing to return if the list happens to be empty. We need that because in Haskell, you would just raise an exception here, but coq doesn't have exceptions. Why doesn't it have exceptions? Because the functional language, as we're going to find out tomorrow or the next day, also has logical content. And so raising an exception would be kind of a funny thing to do in a logical sense. So we don't do it, please.
Are all your functions total in coq?
All functions are total in coq. Let me make one comment about that, and then I see one more question. So all functions are total in coq. There are different ways that can be used to prove that a given function definition is total in coq. The way that we'll use exclusively for the next couple of days is the simple way, which is coq will automatically, so look here, this declaration, let's see, wait a minute, this is tail, so this is not interesting enough. Let's go, oops, let's go back to length. So here we make a recursive call to length. How do we know that that recursive call will always terminate eventually? Because this t is a pattern variable that was obtained by pattern matching against the L that's the argument to the function that is in the same position as the t here. So it's just syntactically obvious that t must be a subtree of L. And this is exactly the reasoning process that coq's termination checker does. There may sometimes be recursive functions that do always terminate, but that you can't see it by this kind of very simple sub-expression reasoning. And for that, coq has more sophisticated facilities where you can attach a termination measure, which you later prove is actually decreasing. Okay, so I'm not going to show you that. I'm just letting you know that it's available for the time when you will get to eventually where you need to use it. But actually, the simple termination measure plus just learning to program in a style that it can recognize will get you very far. More questions? Yes, please.
The usual termination is done automatically by the coq?
Yeah. So coq is so when you're using the simple termination checker, the checking is completely automatic.
And if it's not automatic, then coq will ask us to prove, or like we have to.
So what would happen? What would happen if we made a mistake? So for example, what would happen if we put L here instead of T? We would get an error message of the form, I can't show that something is going down. And then we could switch to the other style. Other questions, please.
So between the slides, you've been switching between fixed point and definition.
Yeah.
And fixed point is in particular for recursive functions. So why not just uniformly use fixed point in place of definition?
Okay, so I've been switching between definition and fixed point, depending whether the thing I'm defining is really recursive or not. Could I just use fixed point everywhere? Yes, I could.